couple different choices for gamma, which would both satisfy. All right. He says, what we have found here is a modified division theorem for z. He said, usually integers a and b with b not equal to b not equal to 0. The division theorem in the integer says, take bq to be a multiple of b, which is nearest to a from the left. And then you set the remainder, blah, 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 so that the remainder is positive. And the remainder will be less than the absolute value of b, which is what we proved earlier in this course. He said, but in the modified division theorem, you just take bq to be the multiple of b, which is closest to a, right? And that might, make your remainder negative. But in absolute value, it's still going to be smaller than b. But anyway. All right, so now the proof, right? Now the proof. By the way, this is how we do division in the Gaussian integers. We have to calculate like the complex fraction and then look for decimal equivalents and then pick the closest point. Yeah, this is going to be proof of theorem 3.1. So here I will begin. And I'm pretty much going to follow Conrad line by line because it's just beautiful. We have alpha and beta in the Gaussian integers, all right, with beta not equal to 0. All right. We wish to construct what? Gamma and rho in the Gaussian integers such that alpha equals to beta gamma plus rho, where the norm of rho is less than or equal to 1/2 the norm of beta. So starting, it's actually going to mirror the calculation that we just did in the example. I really like this proof. It says write alpha over beta alpha beta bar over beta beta bar, right? Which is equal to alpha beta bar over norm beta. And we're going to call that m plus ni over norm beta. All right? So we set m plus ni equal to alpha beta bar. All right? He says, next, divide m and n by n of beta using the... He says, divide m and n by the norm of beta in Z using the modified division algorithm. In other words, that one where you seek the smallest remainder in magnitude, not a positive remainder necessarily. All right? So like for this example I had over here, the remainder wouldn't be 7. We would choose remainder minus 2 because it's a smaller remainder, yeah, in magnitude. All right, and write thus there exist Q1 and Q2 in Z, and 0 less than or equal to the norm of R1, norm of R2, less than 1/2 the norm of beta. Do you understand that? Do you understand why it's 1/2 the norm of beta?
From that thing previously?
It's talking about the modified algorithm. So I'm going to erase this calculation here because we're done with it. So, we're talking about, let's see here. I guess I'll stick with this. So, here's M somewhere, right? And then you have multiples of n beta, right? So maybe this is q times n beta, and maybe over here you have q plus 1 times n beta, right? So if you're choosing the multiple closest to the number to implement the division algorithm, and the distance between those two things is the remainder. So if you look at that, so we choose this one, right? So it's this distance. But if you think about it, no matter where the point lies, it can't be more, like if you pick the closest one, it has to be within half the distance between the multiples, right? And the distance between these multiples is n of beta, right? So M must be within 1/2 n of beta from its nearest multiple. So that's why I get to put 1/2 n beta here from the modified division algorithm. I mean, look at this. I erased the example. The one I had written, what were we dividing by?
Oh, I have it. We were dividing the original thing.
We had 34 is 9 times 4 minus 2. 34 is 9 times 3. We're dividing by 9, right?
Mm-hmm.
So the 7, the positive remainder, bad choice, larger than 4.5, right? But minus 2, magnitude, smaller than 3.5. That's what I'm talking about. Okay, so, and what's the punchline here? Move along, move along. We have M is equal to n beta q1 plus r1, right? And n is equal to n of beta times q2 plus r2. Again, by the modified division algorithm, right? Then what? We calculate. So alpha over beta is what? It is n beta q1 plus r1 plus n beta q2 plus r2, all times what? Remember, it's m plus ni, so that's n, so we have to multiply by I. So this numerator, I'm just writing out m plus ni in light of what we just received from the modified division algorithm. And that's supposed to be divided all by what? N a beta, right? Ooh. Ooh, yeah. So we got the n betas cancel. And we got ourselves a what? Q1. I'm going to write it. Q1 plus IQ2, right? Plus R1 plus IR2. Right? And oh, I should be careful. Can I just let me not be a typical intermediate algebra student and just make that cancellation. My bad. For shame, for shame, for shame. Can we just do that? No. We can only cancel where it is, right? There's still a n beta here in there. Duh. Dummy. Me, not you. All right, so we set gamma equal to Q1 plus IQ2, right? And what are we going to do? And he says, after a little algebra, Oh, little algebra. Little algebra sounds like I need more board space, right? I refuse to do a little algebra at the bottom of a board. Never goes well, right? So he says, okay, so then alpha minus beta gamma. All right, so we can work that out, right? What's our alpha?
R alpha.
I mean, alpha is whatever it is, I suppose. How do we have things broken down?
Alpha is by plus p.
That's what we're trying to work to. We said gamma equal to q1 plus q2i. He says after a little algebra the above equation.
He says q2i.
Yeah.
Put alpha on the other side. I don't know where to get beta.
Well, let me start. He says he's modifying the equation. So let me write the equation down again. So we have alpha over beta, right? And he says q1 plus q2. We're gonna call that gamma, right? And plus R1 plus IR2 divided by n beta. Well, n beta is what? It's beta beta bar, right? So let's do that. And okay, so multiply this equation by beta. We get alpha equals to beta gamma plus R1 plus IR2 divided by beta bar, right? Multiplying by beta, which then gives us the equation that he writes, which is that alpha minus beta gamma is equal to R1 plus IR2 divided by beta bar, right? And he then says, set this equal to rho, right? This is going to be our rho. Right, if we make that rho, we have satisfied the algebraic aspect of the division algorithm already. Now we just need to do what? We need to show that the norm of rho is in fact less than 1/2 n beta, right? Norm of beta. All right, so let's go through that. He says let z equal to R1 plus IR2 divided by beta bar. So z beta bar equals R1 plus IR2, okay. Not sure where he's going with this. So he's like, okay, so then the norm of z times the norm of beta bar is equal to the norm of z beta bar, right? By multiplicative property, which is the norm of R1 plus IR2, which of course is equal to R1 squared plus R2 squared. All right. I'll buy that. He says the norm of beta bar is equal to the norm of beta. Well, I'll also agree with that. Since the norm of beta is equal to the norm of beta bar, the norm of alpha minus beta gamma is equal to what? Yeah, I mean, that should be, I would say it's the norm of R1 plus IR2 divided by beta bar, right? Which is equal to the norm of R1 plus IR2 times the norm of 1 over beta bar. Confession, the norm still makes sense for reciprocals. Go back. I don't think you need to do that here.
Well, that's because you can just take the time to get out of the game.
Yeah, fair enough. We could just, yeah. So you're saying multiply this by beta over beta? And if I do that, I get,
No, well, you can break it up first and then just multiply that norm by beta.
but if I do that,
Oh, it'd be beta norm. Okay, I see what you're saying. Pull out a beta.
what I'm saying is that would give me norm, this would give me norm of, good grief, how to say this without writing a ton. So that would give us, by the multiplicative property, norm of R1 plus IR2 divided by beta beta bar times the norm of beta, right? But this is R1 squared plus R2 squared. Technically, it's, good grief, R1 over beta beta bar squared plus R2 over beta beta bar. Remember, beta beta bar is just a number, an integer, right? So that's what this looks like. But what you're looking at is norm of beta squared in the denominator, right? So that cancels with the norm of the beta in the numerator and just leaves you with what he writes, which is namely R1 squared plus R2 squared divided by norm of beta. All right? So let me summarize. We have shown that the norm of rho, which is equal to alpha minus beta gamma, is equal to R1 squared plus R2 squared divided by the norm of beta. And then he says, feed the estimates that we know about R1 and R2 into that, and what does that give us? This is less than or equal to what? See, yeah, so we have, notice that this would give us like R1 squared less than or equal to 1/4 and beta squared, right? Mm-hmm. So we get like 1/4 n beta squared plus 1/4 n beta squared from the other one, all divided by n beta downstairs. What's that give you? That is 1/2 n of beta. And that completes the proof. So let me tell you what's coming up. So next we'll look at more examples of division in Gaussian integers, and we'll start talking about like the relative primeness of Gaussian integers. There's a Euclid's algorithm for Gaussian integers. There's Bezout's theorem. There's the greatest common divisor, Bezout's theorem. And what else here? More and more divisibility results. Or results about relatively prime. And anyway, once we get through this, what we will do is we will apply this to primes of the form 4n plus 1. And we'll show that we can analyze all of the primes, right? And because if you think about primes, they're either even, right, or they're odd. The odd primes either fit into the case 4n plus 1 or 4n plus 3. And what we're going to learn is that the ones that are of the form 4n plus 1, if I remember right, those can be rewritten. Those can be written in the form a squared plus b squared. But I hope I'm not getting it backwards. I always hate when I remember a theorem like exactly backwards, you know. But on the other hand, the primes of the form 4n plus 3 cannot be written as a sum of squares. And we also find really interesting things like, things that aren't prime, you can write as a sum of squares in 2 different ways. We're going to see a calculational technique to write, to create numbers they can be written as sums of squares in as many ways as you like. Like I could construct a number that can be written as a sum of two squares in 10 different ways. And I could control the ways.
A sum of two squares?
Yeah, a sum of two squares, but 10 different pairs can achieve the same number.
It sounds impossible.
It can be done. We can construct it. We can make it happen.
Like Gaussian integers?
No, regular integers.
No.
But we're going to use Gaussian integers to do it.
Oh, okay.
That is the...
I'm thinking natural numbers. Let's just, no.
No, I'm talking about natural numbers. There are...
Like all, you can't have two sums of squares that equal the same number that are all natural.
Yeah, you can. Let's see here. Let me try to come up with one. Oh, sorry.
I should just get them.
You're fine. Let me try to come up with one. I don't know.
Now I understand.
How about 60? Does 60 work?
I'm not sure. 49. No, can't do that. 25 and no, that doesn't work. 16 and 16 and 40 and 64.
Let's start with one that we know.
60.
60.
64 and minus 4 squared, or minus 2 squared. 8 squared minus 2 squared.
So let's go with 68. 68. It's like you said. It's 8 squared plus 2 squared, right?
I said to get 60, it's the other way around. Just minus it.
But I can't minus. I have this add.
Oh, okay. Oh, yeah, sum. Uh-huh.
Is there another way you can get that as a sum of two squares? I mean, I'm not sure. I just made it up. I should just look at. What am I doing? He has examples.
I get it now. My brain was very one track minded.
But anyway, we'll see you next time.
No, but I understand what you mean.
I'll stop here.